So welcome everyone to this session on using or not using reactive streams in the recent Java versions. My name is Jacek Kunicki. I work at Software Mill. We're a consultancy based in Poland. We write code like most of you do, but there are two things that are unique about us, I think. The first one is that we work only remotely, so we don't have any office. And the second one is that we have a flat structure, so no managers internally. We have like kind of democracy. If you'd like to learn how it works or how it does not work, please feel free to catch me after the talk. You can also catch me to talk about reactive streams, of course. So before I talk about reactive streams in Java, let's just start with a quick recap of what reactive streams actually are. So when talking about stream processing, I'm pretty sure that most of you are familiar with the overall architecture of a stream processing pipeline. So you usually start with some source of your data. You can call it a producer. Then you have some destination for your data that you can call a consumer, and you have a couple of stages in the middle that do something with your data, probably some kind of transformations. And of course you have data flowing from the producer through the stages and to the consumer. So actually when you look at this, and you wonder what could go wrong in such a scenario, then you can imagine that the party that is downstream, so like one of the stages, for example, is much slower than the party that is producing data. Because if it's the other way around, I mean the producer is slow and the consumer is fast, there is actually no problem. But in the opposite situation, where the consumer is slower and the producer is fast, you have some excess data that you need to deal with somehow. And there are, of course, a couple of ways to deal with it. Well, for example, what you can do, you can just drop the excess data. So if there is too much, you can just not process it. And strange as it may sound, it actually happens in some scenarios, especially in some lower level network hardware, for example. So that's not the level we typically work with on a daily basis. But in the network code, it's like pretty obvious to just drop the excess data. The other thing you can do is to block. So the thing that is processing the data is not accepting anything, and is basically blocking everything until it's done processing. But this is also not a good solution because, well, you want to be asynchronous, you want to be non-blocking actually instead of blocking. So to block is not the way to go. Another way to deal with this excess data is to buffer it. So then either the producer can buffer it or the consumer can do it. But then the problem is that buffers are in memory, the memory is limited, so if the producer is really fast and the consumer is really slow, at some point you're going to reach the capacity of your buffer and it's basically going to blow out. So there is one more way to deal with the excess data, which is specific to reactive streams, to this approach, and this is called backpressure. Backpressure, in other words, is you can call it propagation of demand. So in a reactive approach, it's actually the consumer that is signaling to the producer how much data it wants now. So it can say like, give me 5 more elements. And then the producer is obliged to give those 5 elements and no more. So if you think of data flowing from the producer to the consumer like this way, then you can think of backpressure as some kind of signal flowing in the opposite direction. And this is basically signaling demand. And the important thing here is that the demand is propagated from the very end to the very beginning. So, for example, if you imagine a scenario where you're reading things from a file and then storing them into a database, and then the database becomes slow, the demand is propagated until the very beginning, so until up to the component that is actually reading from file, and then it starts to slow down. It's not sending the data. So it's important that it's like not only between two components that are next to each other, but it can propagate from the very end to the very beginning of the pipeline. So reactive streams is basically a standard. There are, of course, numerous implementations of that. Every implementation has its own naming. So in the JDK interfaces, the producer is called the publisher, the consumer is called the subscriber, and the things in the middle are called processors. Now, if you look at this architecture, this is, although you already have backpressure, this may not yet be reactive. For it to be reactive, it has still to meet some other criteria. So the criteria are, the first one is that it needs to be asynchronous. So in the reactive world, you really want not to block, you want to be asynchronous. And also you want not only to asynchronously process the data, but you also want the backpressure mechanism to be asynchronous and non-blocking. Because if you process data asynchronously, but the backpressure mechanism was blocking, then you're still blocking. And the goal is, of course, to reuse any resources whenever it's possible. So be it a CPU thread, be it a machine that is somewhere on your grid, then you just want to make it free when it's not actually necessary. The other important thing about reactive streams is that the fact that the consumer can be slow is somehow represented in the domain model. So I have two examples for that. First one is the Twitter API. So Twitter has a couple of APIs, but there is one that is supposed to be used when you want to stream all the tweets, or filtered by a hashtag, whatever. And then when you use this API, Twitter is allocating a kind of buffer on their site, and they are just sending you data. But apart from sending the data, they are also monitoring the speed, so how fast you are consuming the data. And if your processing speed becomes too low, so if you're too slow, basically, they, instead of sending you data, they are sending you some kind of signals that, hey, you're processing too slow, you need to speed up, because otherwise it's going to be disconnected. So, and this is actually not about how it's implemented internally, it's about the fact that a slow consumer is somehow represented in the API documentation. So they have thought of it, they have a solution for that, and they know that probably something can be slow. Another example comes from Akka Streams. And Akka Streams is one of the implementations of the Reactive Streams interfaces. And in Akka Streams, you have a couple of predefined stages that do something to your data, and one of them is conflate. Conflate, basically what it does is it somehow monitors the downstream, so the things that can be slow at the end of your pipeline, and it lets you deal with the fact that the speed is too low here. So then you can actually specify your own behavior, so you can drop data, you can aggregate it. If it's numbers, you can, for example, sum them, and then when the downstream becomes faster again, you can just send some kind of aggregated data. And once again, this is really not about the implementation inside, but this is about the fact that when you read the API docs for Akka Streams in this example, you already have the notion of the fact that something can be slow, and there is a way to deal with it. So this is the quick recap of Reactive Streams. And as you may know, starting from Java 9, the Reactive Streams interfaces have become a part of the JDK in the form of the java.util.concurrent.Flow class and the interfaces there. So the interfaces are not new actually, because previously you could just use them from the org Reactive Streams package, but then starting from Java 9, they have become a part of the JDK itself. So let's see what the interfaces are. First one is the publisher. So publisher, as you may guess, is something that produces data and sends data to some subscribers that the subscribers consume, basically. And it exposes a single method called subscribe that the subscribers can use to connect to this publisher. Well, then you have the subscriber. And the subscriber, it's pretty obvious that it connects to the publisher and can receive data from it. But there's also a couple of other things it can receive. And so actually first it receives a confirmation of the subscription, so of the fact that it was connected with the onSubscribe method. Then it receives the actual data with the onNext callback. It can also receive errors and completion signal using the onError and onComplete method. So this is like the source of your data, the destination, but if you try to link them together, you use something that is called a subscription. And subscription is a critical component, and this is like most important interface, I think, because, well, it connects to the publisher and the subscriber together. But this is the part that lets you use the backpressure mechanism, because it exposes the request method that is used to propagate demand to the publisher. So you can say that you want to receive a given number of elements. So this is like subscription is the place where the actual backpressure takes place. And also you're able to cancel the subscription, so basically to disconnect those two when they were connected previously. And then if you combine a publisher and the subscriber into a single component, you get something that is called a processor, and it basically has an input and an output. So this is a publisher and the subscriber connected together. So the goal of those interfaces is to have a flow like when you have a publisher, you can call it or subscribe on it and connect to a subscriber, and then you receive the subscribe callback, then you can receive an arbitrary number of onNext callbacks with data, and then you're either completed or you have an error. So the interfaces are pretty simple, as you can see, and we as developers, when we see such simple interfaces, what we think is, let's try to implement them and see if it works. So here we have a simple publisher that it's going we're going to try to implement one that implements the publisher, sorry, from the Java interfaces. It's going to take an iterator of numbers and basically trying to publish those. So in a very naive approach, when you have this iterator and you just want to send the elements to the subscriber and just complete, what you do is you take the iterator, you can use the for each remaining method, and then you take the subscriber, and you call the onNext callback, which is used for sending data. And then when you're done sending, you can call onComplete to signal that you are completed. So this is our first naive implementation of a publisher. Let's try to run it. First, we need to write a main method to be able to verify it. So here's our main method. We're creating a simple publisher with 10 elements. We're calling subscribe on it. And here we need an anonymous implementation of a subscriber. It has a couple of methods, as you saw on the slides. We are interested in implementing 2 of them just to do some output to the console that something is happening. So we are going to implement onNext to have the item that was received actually, and we want to print when the stream is completed. Yeah, and that's it. So let's try to run it and see what happens. Yeah, so you can see that, well, the 10 numbers were actually sent to the subscriber. It received them, it printed the completion signal. So it may seem like we're done, but like you may have something in the back of your head that, well, maybe it's not totally right. So actually, on the slides, I described the backpressure mechanism, so the demand propagation, and actually you can't see anything of the backpressure implementation here. So this is basically taking all the elements, sending them all at once, and then completing, which is, well, not really reactive. And actually, we have a way to prove it, that it doesn't actually fit, it's not a correct implementation of the reactive interfaces. And to prove it, we have something called a TCK, or Technology Compatibility Kit for Reactive Streams, which is basically, well, first of all, it's a set of rules that a correct implementation of reactive streams needs to adhere to. But apart from the rules that you need to follow, there's also a test, a couple of tests that you can run against your implementation of the reactive streams to see whether they are correct or not. So here we have a test for our publisher. It uses the Flow publisher verification, which it's a bit truncated, but you can see that this is from the reactive streams TCK. So let's try to run this test against our publisher and see what happens. So, well, you can see that it's not too optimistic. I mean, most of the tests have failed. There is a single one that has passed, actually, but it says that we need to throw a null pointer exception on a null subscriber. And actually, well, we accidentally are doing it because here in our subscriber, here in the subscriber, if the subscriber is null and we call onNext, a null pointer exception is going to be thrown. But otherwise, the tests are failing. There is actually a test at the very bottom that is still running, so perhaps something is very wrong here. So let's try to look at the tests that were actually failing, and let's try to fix them. So here the numbers that you have in the test names actually refer to the number to the specific points in the reactive streams TCK specification, so in the rules that you need to follow. So let's start, for example, with this one, the 109, but the one that is failing. So this says that when a non-null subscriber is connected, we need to call onSubscribe on it. And that's actually what we didn't do. So let's try to implement it. So now I'm going to fold the main method because we won't be using it. It turned out that it's not really good. So this code is probably also not good. So now they want us to call onSubscribe when the subscriber, well, if the subscriber is null, it would throw NPE, so we are fine there. If it's not null, we're calling onSubscribe. And here you can see that we need the subscription. So here is the missing link between the publisher and the subscriber, and this is the place where the backpressure mechanism is actually going to take place. And we don't have a subscription at hand, so we need to implement it. Let's call it a simple subscription. And so inside the subscription, we'll be handling the backpressure somehow, and this will be the place where we'll actually be sending data. So we need to pass the subscriber there to be able to call to use the onNext callback on it to send data. Okay, so here's our subscription class. We're going to create a field for the subscriber. We are going to implement the missing methods. And as you may remember from the slide, there are two methods in a subscription. First one is request, so this is the one that is used for the backpressure mechanism. And the other one is cancel, and this is used for basically terminating the link. So now inside the request, we basically, we receive a demand from the downstream, and we need to send an element basically. So this sounds pretty simple. We can do it with a for loop basically. So we create a demand variable, initialize it with n. Our condition is, well, first of all, that the demand is greater than 0, and also that the iterator is not empty, because if we empty the iterator, we don't have any data to send anymore. Sorry, it's actually, and iterator has next. And we'll be decreasing the demand here. And now what we do here is basically take the subscriber. Here is the place where we use the onNext method, and then we'll be basically sending the next element from the iterator. And now if we're done, we also probably should be sending the completion signal. So after we've sent n elements with the for loop, we need to check whether our iterator is empty or not, and if it is, we want to signal completion. So if the iterator doesn't have any element, we are going to say subscriber on complete. So once again, what we did here was to implement a subscription, so the link between the publisher and the subscriber, and we implemented the request method, which is actually responsible for handling the demand from the downstream, and we are not yet implementing the cancel method because this will going to be the next step. So here in the request, in the request method, we basically created a loop that is sending n elements, and if it exhausted the iterator, then we are also sending a completion signal. So let's run our test once again. And now you can see, well, that some more have passed, so it's not a single test anymore that is passing. We have some more passing, and specifically the one we were trying to fix is passing. So looks like so far so good, and we're there. So if we are doing such a good job with fixing this implementation, let's try to find another place to fix. And for example, there are two places that seem pretty simple to fix. And they are basically about requesting a 0 or a negative number of elements. So if in our request method we receive a 0 or negative, we want to signal illegal argument exception. So this sounds pretty simple as adding an if statement here for the n. So if n is less or equal to 0. And now, what do we want to do actually? So initially, you may think that you just need to throw this illegal argument exception, but this is not the way to go, because actually the way of signaling errors in reactive streams is using the onError callback, not by throwing exceptions, because just throwing exception won't work. So actually, what we need to do here is to use the onError callback. And here we're just creating our illegal argument exception and sending it to the subscriber. So let's see if it helped. Yeah, so there are two more tests that have passed, specifically the 2309 cases that were dealing with the negative or 0 demand. Okay, so far so good, so let's move further. There are another two cases, and if you read the error messages, it says that when a finite stream terminates, we need to signal completion here. And in 107, actually, after we signal that the stream was completed, we should not be sending any more elements. And in the error message, you can see that we have an additional complete signal, and here the problem is the same. So now we need to remember that this is running in a multi-threaded environment, so you're probably not thread safe in our implementation. And what we need to do here is to fix the thread safety, basically. So let's try to do it. So probably to be able to take notion of whether we terminated or not, we would need some kind of a flag for that. And since we want to be thread safe, this should be atomic somehow. So let's try. Private final, an atomic boolean for that. Let's call it terminated. And we're going to initialize it with false, because, well, initially we're not terminated, we are doing something, and only then we may want to flip this flag to true and signal termination. So now we need to use this flag somewhere. So probably the most obvious place to use it will be in the cancel method, because here if we receive the cancel callback, we want to flip this flag to true, because that's receiving cancel basically means that our job is done and we terminated. So we set it to true here. And then we need to use it in two other places, where first of all we need to extend our condition whether to send an element or not with on next. So now we not only want our iterator to be non-empty, but also we don't want ourselves to be terminated. So here comes another condition, and it's not terminated.get. So before we send anything, we're checking whether we're not terminated. And the other place where we need to do it is also to not to send a duplicated completion signal. We also want to check it before sending on complete. So here we also add the condition of terminated being set to false. And actually, if we are completing, we should also indicate that we are now terminating before sending the completion signal. So we are setting that to true. Now, if you look at the code, it's like the logic seems correct, but if you think carefully that you're in a multi-threaded environment, this is really not an atomic operation, because here you are checking whether the flag is set, and then you are setting into true, and this can still result in a race condition. But actually, atomic Boolean helps us with that, because we can do these two things in a single method. So instead of calling get and set separately, we have a get and set method, which does the two things, but it does it atomically. So basically, first we fetch the value for comparison in the if statement, and then after fetching it for comparison, we're setting it to true, and it's done atomically. So once again, what we did there is basically we added some state to our publisher, and the state is a flag that says whether we are terminated or not. And we are using it in three places. Well, first it is set in the cancel callback when we are indicating that we're terminating. Then we are using it as a part of the condition whether to send the next element or not. And the last place where it is used is before sending a completion signal, so that we guard ourselves from sending duplicated completion. So let's see if it helped. Yeah, so now it looks much better, because there are actually only two tests that were failing from a couple of them. So now if we look at the messages, well, the first one is about something called unbounded recursion, which is basically that we are doing something infinitely, and we shouldn't be. And the other one is, well, we have a Stack Overflow here, so we've run out of something. And this is about requesting very large number of elements. So very large meaning like long max value. And actually, this is the moment where we are hitting the wall a bit, because now this is not that easy to fix these errors correctly. So we have some further challenges that are here. And the challenges are, as you could see, first of all, is the unbounded recursion. The problem is that our implementation is synchronous. So if we receive the request callback, then we are calling on next on the subscriber with the elements. And then what the subscriber would do after processing these elements would be to call request once again. So you are basically getting into this request on next cycle, which gets called infinitely. To solve it, we would need some kind of an asynchronous implementation that would do it correctly, but this is not trivial anymore. It's not as trivial as the fixes that we applied previously. And the other problem, as you could see in the error message, was handling infinite demands. So, for example, if we receive a request long max value and then we receive another one like that, so that's requesting a lot of elements 2 times in a row. And then if our implementation was asynchronous, so let's say we tried to do something naively, something like creating a new thread for every request callback, then of course if you requested long max value threads, probably you're going to run out of resources in your system, so it's not going to work. And if you did some other implementation, which would probably accumulate the demand and then somehow fulfill it, then if you thought of just storing it in a variable, it's also not going to work, because if you had a long to store this demand and then you received request long max value twice, then you are going to basically overflow your long value. So this is still not going to work. So as you can see, this is really not trivial, and the takeaway from this, from trying to implement this ourselves, is that you shouldn't be really doing it unless you know what you are doing or unless you're implementing a library. But what the interfaces are there for in the JDK is really not for implementing them on a daily basis and not creating your reactive streams implementation every time. And actually, the goal of the interfaces is to provide something called an SPI, or a service provider interface, which is basically a way to connect different implementations of those interfaces together. So you can imagine that you have a couple of implementations of the reactive libraries, and you want to bring them together so that they have unified interfaces to communicate with. Now, if you look at the JDK, and if you look at the existing abstractions related to stream processing, maybe not directly, but still in some way, there is a couple of them. Well, first of all, you have the input and output streams for files, which even the name tells you that this is about stream handling. You have iterators, which is not directly related to streaming, but this is still the concept of having an infinite source of data, which sounds like streaming a bit. You have channels in the new I/O for files. You have servlets with read and write listeners, and this is once again handling of possibly infinite stream of data. You have results sets in Java SQL, and the result set may be backed by a cursor in the database, for example, and then this is once again fetching an unknown number of elements. So this is also a bit of a streaming approach. You have streams that are there since Java 8, and of course you have the interfaces that we just described in the java.util.concurrent.Flow. So the problem with those is that they are really not unified. So it's, for example, hard to connect them together. It's even hard to, for example, transfer data from a single file, from one file to another using a reactive approach, because if you wanted to do it with the input and output streams, you actually would need to allocate a buffer yourself, then read some data, store it in the buffer, then write it to the other file. And what we would like to do using those interfaces is to use this one single call, publisher.subscribe, with the subscriber, to be able to connect those implementations together and use all the goodness that is inside. Because this is a single call, so publisher.subscribe, but underneath you have all the goods of reactive processing, especially the backpressure mechanism, for example. But we don't have it actually. So what we are missing, for example, from the well, it's not an implementation, it's only the interfaces in the JDK, is something like a minimum operation set. So we only have the interfaces now, and we're even lacking some basic operations like filtering, mapping, so something that you can know even from Java streams, for example. There is nothing like that at the moment. You only have the interfaces. So to solve it, there was like a year ago, there was a proposal from Lightband called Reactive Streams Utils. And the goal of this proposal, well, the idea was to include the basic set of operations like mapping or filtering in the JDK, and then to be able to provide other implementations like the most complex ones, because if you think of most complex processing graphs like parts of the graph that have multiple inputs or multiple outputs, this is usually very specific to a concrete implementation. So then you would be able to basically plug a concrete implementation using this system property, Java Flow Provider. But of course, as everywhere, there is some politics. So there is this battle between Spring and Java EE or Jakarta EE, whose logo is here. So the problem is that, well, in Spring, if you are using Spring and the reactive approach, you already have product reactor inside, so all the monos, fluxes, and stuff. And now there are people who are using Spring, and actually there are some companies that are still using Java EE or Jakarta EE. And probably they would be happy to have something like that built in. So, but the goal is that, well, if no one implements it, then it's not going to be there. So this, and the guys from Spring are not really interested in implementing this in the JDK because they have Project Reactor on board and they are done. And actually there is really no one to implement something like that in the Jakarta EE. So actually, like as a sign of what can happen or what cannot happen, this presentation is like a year old, and this Reactive Streams Utils initiative was created like a year ago But when I looked at it today, and the last commit is from like half a year or even more before. So actually nothing has really changed here, and probably the future is not bright. So if you think of some other places where it would be nice to have some reactive support in the JDK, there are some common use cases. One of them is HTTP, for example. In the servlet I/O, starting from version 3.1, you already have some asynchronicity built in. And actually in the JDK, you have a reactive HTTP client. I'm not sure if you heard of it, because in Java 9 it was experimental. Now I think from 10 it's not experimental anymore, it's there. And it exposes some methods that can take the reactive interfaces. And now if we imagine that the servlet API and the servlet request could also expose the reactive interfaces, which it does not, because this is like just thinking what the future could look like. And if you thought about the task of uploading a file and sending it somewhere else, this would become something like that, because you already have the method that takes the publisher for a post method in the HTTP client, and then if the servlet requests also expose the publisher, you could transfer a file like that with all the goodness of the reactive approach. So with backpressure and all the stuff like error signaling, completion, and etc. built in. But it's important to note that it's not there, so this is like, these are some dreams about the future that I'm not sure are going to be fulfilled. Another use case, a very common one, is accessing a database. So there was an initiative from Oracle called ADBA, or Asynchronous Database Access API, whose goal was exactly to create a reactive connectivity to databases, and it was much more than just returning a feature from JDBC. They were actually trying to implement it from scratch, but it didn't work. So this was announced on Java 1 like 2 years ago, and they were very happy about it, but actually not much has happened since. And they were actually, I think they hit the wall at some point, and they basically were not able to implement it. There is some new hope coming from Pivotal, so the company behind Spring, called R2DBC, or Reactive Database Connectivity. And this is actually something, since it's from Pivotal, it's really made thinking about Spring from the very beginning. So if you're familiar with Spring data, so basically like naming your method so that they resemble SQL queries and then just having queries auto-generated, RDBC could work with that. And this is now actively developed, so perhaps this is something that it's going to be the future of reactive database access. There are, of course, some vendor-specific async drivers, but the problem with them is that they are not unified, and we want all of them to be unified. And now if you thought, if you imagine that in the JPA you have some reactive supports, and you are fetching your users like that, this could be really nice, because normally what you're doing, you are calling get result list, not get result publisher, because there is nothing like that at the moment, and you get a list of users. But if you want it to be reactive, you could imagine that there is a get result publisher method, and it gives you a publisher, so the reactive interface with the users. So this is about JPA, but and that once again it's not there. So it could be nice, but it's not there yet. But not everyone is using JPA. There are people who prefer a simpler approach, and you may be using the library called JOQ, so where you basically write your SQL code, and then it gets you can just run it against the database. And actually, only recently, the creator of JOQ has announced that they are going to support the reactive interfaces in the upcoming versions. So this may be a point where you can like drop JPA, because it's like complicated as all the ORMs, and you don't want the magic. You want to use a simpler approach, and you want to be reactive. So you could then just take JOQ and have your data exposed as the reactive interfaces, which is really nice. There is, of course, more that you could like dream of, or that you could expect from the JDK to provide. For example, some kind of reactive file I/O. So basically having, if you think once again of transferring data from one file to another, if you had a publisher of data from a file and a subscriber to write to another file, that you can just call subscribe and not allocate a buffer yourself, but have it done in the background with backpressure and stuff like that. You could think of JMS, so this is also about like asynchronous processing of stuff, so a reactive support here would be nice. WebSockets is another example, because this is also sending of possibly infinite stream of data to the browser, but still this is the use case. You can think of AWS like uploading a file, and actually they are working on supporting the reactive approach in the AWS SDK. But the problem is that I think they won't be exposing the reactive interfaces directly, but what they would be doing instead is just like using them internally, but the API that would be exposed is not going to be reactive. So you won't have a publisher that sends data to AWS. There is also Project Alpaca, which if you heard about Akka Streams, one of the implementations of Reactive Streams from Lightband, then Alpaca is basically a set of connectors for Akka Streams to different things like databases, queues. You can think of Alpaca as of Apache Camel, so an integration layer, which is done with the reactive concepts in mind from scratch. So it builds on reactive streams, it builds on Akka streams, so you have like a new way of integrating systems with reactive concepts in mind. So now I'd like to show you a very simple example of how we can actually use this SPI, so the interfaces in the JDK, to connect different things together. And since there is really not much to connect at the moment, this would be very simple. And what I'll be doing is I'll take a publisher, which will be written in Flux, so as a Flux, so with product reactor. Then we'll take the intermediate part, so the processor from Akka Streams, and this is going to be an Akka Streams flow. And then we'll use RxJava as the subscriber. So we're basically taking 3 different implementations of reactive streams and demonstrating that they can actually be connected with the interfaces that we have there. So here you can see the example code, and like from bird's eye view, you can see that we have a publisher that comes from Reactor, we have the processor that comes from Akka Streams, and then we have the flowable, which comes from RxJava to like connect this and run as a single pipeline. Now, if you looked at the methods that are actually creating those components, you can see that the types that are returned are actually from the JDK. So the publisher here is the java.util.concurrent thing. But inside, if you look at it, you can see that we are actually taking the Flux from Project Reactor. And then, of course, we need some glue code, because if you create a Flux, it returns a Flux, not a publisher. And if we want to convert it to a Java publisher, we need to use some glue code. In this case, it's called JDK Flow Adapter, which basically lets you convert it somehow. And now it's similar with the Akka Streams processor. So once again, it returns the processor from the JDK interfaces. But inside, you take a flow. Flow in Akka Streams is the component that has an input and an output, so it does some processing of data. Here it does the negation. And then once again, you still need some glue code. Here it's called Java Flow Support, because you don't want to return a flow, you want to return a processor. But it's doable, and eventually you're able to stick to only the interfaces that are there in the JDK. Now here, if you look at the Akka Streams code, you can see something called the materializer, which is related to the internals of Akka Streams, and it actually shows the different approaches that different libraries take. So if you use Project Reactor, you basically create your pipeline, and you don't really care about the runtime underneath. But in Akka Streams, on the contrary, you need to explicitly provide a runtime, and this is the materializer. So you need to create it yourself. The only materializer that exists at the moment is based on an actor system, so basically you have actors underneath. But the difference is that you need to create it explicitly, so Akka Streams doesn't do it for you. So now if we run it, so 0 was not negated, but then the subsequent numbers are actually negated, because our Flux emits numbers, and then our Akka Streams flow negates them, and we are outputting them to the console. So it looks like it's working. So what we did here is we took different implementations of reactive streams, and using the SPI, so using the interfaces in the JDK, we connected them so that it's behaving in a reactive fashion here. Okay, so for a summary, well, you need to know that what you have in the JDK is not a full implementation of reactive streams. It's only an SPI, so a service provider interface, that basically allows you to interop between different components that implement those interfaces. And as you noticed in the first example, it's really not trivial to implement those interfaces yourself, because there are a lot of challenges, and you really need to be careful when implementing that, and you need to know what you're doing. So if you plan to do it yourself, you really should be using the TCK, because the TCK verifies if the implementation is correct, which basically means that if you connect your implementation to another correct implementation, it's going to work correctly. So you're not going to break the backpressure and the other mechanisms. There are some resources. Here is the runtime, the Reactive Streams utils, which unfortunately seems to be dead since last year. This is the TCK, so if you wanted to do something with Reactive Streams, I encourage you to read it, even if you're not going to implement it, because by reading it you can see how many challenges there are, and that it's really not trivial to do it. There is a block entry about ADBA, which also seems to be dead, but well, you can at least read about the concepts. Here is R2DBC, so probably the future of reactive connectivity for databases. And there is a very nice blog series called Advanced Reactive Java, where you can actually read a bit more about implementing those interfaces and doing this correctly, actually. So that's all what I had for today. If there are any questions, I think you could submit them with a form, so the guys here will be asking them. Otherwise, thank you very much for being here.
Thank you, Jacek. Just to remember you that we have a page for all the questions that you want to do. Okay, it was published on the web of the J on the Beach, and you have the URL at the last page of your badge. Okay. So we have one question. Wait. We have one question of one of the attendants. We have heard in your talk that the future is not so bright in the JDK, but is there something in the latest or next version of Java that you find exciting regarding reactive programming?
Well, so as I said, like you can see that some of the concepts that were initially in the JDK are dead by now. But well, the only thing that is nice, I think, is the reactive HTTP client. So it has gone out of the incubator in Java 10 or 11, I think. So now actually, instead of using Apache HTTP or something like that, you can use the built-in reactive client, which at least would let you do HTTP calls in a reactive way. But apart from that, unfortunately, I think not much is happening in Java in relation to the reactive interfaces. So they are still there. There is this HTTP client, but that's pretty much it.
Okay. Thank you a lot. Yeah, that's it.
Thank you.